So the floor is yours.
Thank you, Yanto. Hello, everyone. I'm very excited and very pleased to be back to Hong Kong virtually and give this lecture in this course. So before we start, I would like to introduce a little bit about myself. My name is Shirley. I'm an assistant professor in School of Economics at Utrecht University. But before I moved to Hong Kong, I actually got my PhD from Hong Kong Polytechnic University, and I also get my master's degree from Chinese U. And I do research in social entrepreneurship, emerging technologies, and computational methods. For example, I use natural language processing and computer vision to automatically analyze the big data from online social media platform. So the goal of today's lecture, first, we'll explain what structural equation modeling is. We will discuss some of the key terms in SEM, and we'll also explain why and when do we use it. And next, we're going to discuss the procedure, the concrete steps of conducting SEM. For example, we'll explain some of the details, like how many samples you need, and how, like what indices you need to report, and how to interpret these results. And in the second half of the session, I'm going to show you how to run SEM in R and Amos. So first, some of the key terms you need to know before we dive into SEM, endogenous variable and exogenous variable. So endogenous variable is dependent variable that has a causal path leading to it. And exogenous variable is independent variable that can explain an endogenous variable. So we have example here. We have two IVs, independent variables, technological innovation and workforce diversity, and we have a dependent variable, which is public service efficiency. So in this model, you can see that the endogenous variable is actually the public service efficiency, right? And then the exogenous variable are technological innovation and workforce diversity. And this is endogenous variable and exogenous variable. Next is about latent variable and observed variable. So latent variable is a variable that cannot be observed directly. You cannot measure it directly. You need to construct the latent variable by using some other questions, right? We also understand as a factor, for example, social capital. We cannot observe social capital directly, right? You always need some other indicators to understand, to calculate social capital. And citizen satisfaction and innovation climate, they are all latent variables. And observed variable is also very simple to understand. You can observe the variable directly, like participation in social groups. You can see which social group this person participates in, right? You can observe this directly. Or ratings of public services, you can tell from the number, you can tell from the scores, right? The public service receives, and investments in R&D, you can tell from the amount of money the R&D receives. So latent variable is something that cannot be observed, cannot be measured directly, but observed variable is something that you can observe, you can measure directly. And we can actually understand latent variable and observed variable in a questionnaire setting. So like we have the questionnaire on employees' participation in decision-making, and we have 6 questions to measure this variable, right? So these 6 questions measure different aspects in participation and decision-making, and these 6 questions are actually observed variable, right? You can directly tell from participants' responses how many scores each question receives, right? And then together, these 6 questions construct the variable participation decision-making, right? So participation decision-making is actually a latent variable. And this is latent variable, observed variable, and endogenous variable and exogenous variable. So what is structural equation modeling? By definition, structural equation modeling is a linear model framework that can model both regression equations with latent variables. So you can already think of many possibilities of different models, right? So by saying this, SEM is not a single statistical technique, but it's more like an umbrella term for different types of techniques, right? It can be single or it can be multiple regression. It can be multivariate regression. It can also be path analysis. It can be confirmatory factor analysis or exploratory factor analysis. It can also be structural regression, right? There are many possibilities. And how do you differentiate different types of techniques? So we need to check how many endogenous variables, how many dependent variables are involved in the model, and whether they are observed variable or latent variable. So it's also very important to be clear and to be specific about which type of SEM you're using. You cannot just say, I'm using SEM, because it's very broad, right? So you can be very specific on which type, like, are you using path analysis? Are you using confirmatory factor analysis or other types, right? And the most important thing here is you need to know is that the basic statistic or the foundation of SEM is covariance. And covariance is very important for you to understand the characteristics of SEM and what you can do with SEM and what you cannot do with SEM. And we will explain this later. Here is an overview of the SEM family. So you can see, depending on how many endogenous variables your model has, whether it's one endogenous variable or it's two or more. It can be simple regression, multiple regression, or multivariate regression, path analysis, factor analysis, or structural regression, right? And in, for example, if you have two or more endogenous variables, we also need to see whether it's the relationship from endogenous to endogenous, or it's from latent to observed, or it's from latent to latent. We can differentiate them based on these different factors. So first, simple regression. It's very simple to understand, right? It only has one endogenous variable and one exogenous variable. And for multiple regression, it has more than one exogenous variable, so which are two or more independent variables. So simple regression and multiple regression, they both only have one dependent variable or endogenous variable, right? And if your model has two or more endogenous variable or dependent variable, it can be multivariate regression here, or path analysis or other possibilities, right? And here, we can see that it has Y1 and Y2 as the dependent variable, but we can see that Y1 and Y2 here is a double-headed arrow, right? Which means that Y1 and Y2 are interrelated. So this is multivariate regression. In multivariate regression, the dependent variables, they are interrelated. So imagine that we don't have the double-headed arrow here. Then it's just like two separate regression, right? One simple regression from X1 to Y1, and one multiple regression like X1 and X2 to Y1, right? So it's two separate regression if we don't have the double-headed arrow here. But if we have it, then it's multivariate regression, which means that we need to consider the joint distribution of the DVs. And we want to estimate how the changes in the IV, in the exogenous variables, are associated with the changes in the entire sets of the DVs. And we have an example to help you understand a multivariate regression. For example, we have two IVs, advertising exposure and the product quality as the two IVs. And then we have brand loyalty, we have purchase intention as the two DVs. And these two DVs, brand loyalty and purchase intention, they are interrelated, right? So in this case, we need to use multivariate regression to model the relationships among these four variables. And we also have path analysis. And these two models are very similar, right? So the only difference is the direction from Y1 to Y2. So in multivariate regression, you can see it's interrelated, it's double-headed arrow, but in path analysis, it's one direction from Y1 to Y2. So in path analysis, we actually have the relationship from endogenous to endogenous, which is from one dependent variable to another dependent variable. So this is how we differentiate path analysis from multivariate regression, right? All clear? Is there any question you want to ask? If you want to ask, you can react on Zoom, and then we can see you're raising your hand. If no question, then we continue. So here is vector analysis. So in this model, the rectangles are actually observed variable, and we have round shape here, and here they are latent variable, which cannot observe directly, right? And we in vector analysis, we have more than one endogenous variables. For example, we have y x1, x2, x3. They are endogenous variables, and they also have from the relationship from latent x to observed, from x to x1, from x to x2, and from x to x3, right? So you might be wondering, like, why the direction, why the arrow here is from x to x1? Why it's not reversed? Why it's not from x1 to x, and then x2 to x, and x3 to x? So why is the from latent to the observed? I will give you 30 seconds to think about it. Why is the direction like this? Is there any answers, any thoughts? Actually, the latent variable here, x, is a theoretical construct, right? It's something that cannot be observed directly. So, and we want to assume that the changes in the latent variable can cause a systematic variations in the observed variable, right? We want to, because each of these observed variable is related to this latent variable x here, right? So we want to see how the changes in x cause or influence the variations in the whole set of x1, x2, and x3. So you can see the direction is from x to x1, x to x2, and x to x3. So so the arrow here is from latent to observed, right? And we also have the three arrow terms here. And why do we use vector analysis? So the primary purpose of vector analysis is actually to model and capture the shared variance among these observed variable. And we assume that this shared variance by these observed variables are because of their shared associations with this latent variable, right? And when do we use vector analysis? Most commonly, we use vector analysis to validate the scale or the measurements you use in your study. So you want to see whether it's reliable or whether it's valid or not. And we use vector analysis to do this. And then we also have structural regression. So it's a very complicated model, right? You can see it has the measurement part, like the vector analysis we saw just now. And it also has the structure part, which is about the relationships among these three latent variables. So x, y, z here are latent variables. And by using structural regression, we want to capture the whole model here, like both the measurement part as well as the structural part. So we use structural regression to do this. And how do we conduct SEM? Like, what is the first step? Actually, before we talk about the first step of conducting SEM, we need to understand the goal of SEM. So the goal of SEM is actually to assess how well your hypothetical model, your hypothesis, fits the data. So by saying this, we need to have a hypothetical model, right? You need to start from a theory. You need to start from your hypothesis. So doing SEM is also a hypothesis testing process. The theory can be structural theory, which is about the relationships among different latent variables. It can also be a measurement theory. It's about something like you want to see whether your skill can measure the vector well or can measure the latent variable well, not right? Or you can combine measurement theory and structural theory. And but we also need to be aware that like using SEM alone cannot demonstrate, cannot infer causality. And think about why. Because in the model, we can see there is direction already, right? From one vector to another. Why we cannot infer causality here? This is because we already said that the basic statistic of SEM is covariance, right? In covariance, there's no direction, right? So you cannot use SEM to infer causality. And we always need to complement SEM with other ways. For example, you complement it with experimental design. So you can combine the experimental studies with the SEM to infer causality. It is possible to infer causality if you combine it with experimental design. But if you just use SEM, you can't just say there is a causal relationship between X and Y. Yeah. So this is something that we need to remember. And next, if you have already identified your model and you already select what type of measures or scale you are using in your study, and you need to start to collect data, right? But how many samples do you need? Actually, we follow the N to Q rule. N is about the sample size and Q is the number of parameters in your model. So the ideal ratio of N to Q is 20:1, which means that if you have one parameter in your model to estimate, then you need to have 20 samples. And the minimum ratio of N to Q is 10:1. So you need to, if you have one parameter to estimate, then you need at least 10 samples to have adequate power. And after you collect the data, you analyze the data, you need to think about which indices you need to look at, like to see whether it's a good fit or it's a poor fit, right? There are several indices you need to report. For example, we have chi-square. So chi-square is about the discrepancy, the difference between the observed data, so from data and your hypothetical model. So it's the difference between what you observed from the data and what you hypothesize in the model, right? And we always want smaller chi-square value, but chi-square can be very sensitive to sample size. And we also have degrees of freedom you need to report and p-value, right? And degrees of freedom is about the number of free parameters estimated in the model. So it is calculated as the difference between the number of observed variables and the number of estimated parameters. So we also use degrees of freedom as an indicator of model complexity. And p-value. P-value is about the probability that the observed discrepancy, the observed difference between the model and the data is occurred by chance alone. And a smaller p-value indicates a lack of fit between the model and the data. And why is the opposite to what we know about, like when we do significance testing in regression, we always want a smaller p-value, right? But in SEM, we want the opposite. We want a larger p-value. So why? You need to think about why. It's because chi-square test in SEM is a hypothesis testing process, right? We have the null hypothesis, which is we assume that there is perfect fits between the model and the data. this is null hypothesis. And if you have a significant p-value, like smaller than 0.05, which suggests that you need to reject the null hypothesis, right? We need to reject there is a perfect fit between the model and the data. So this is why this is why a smaller p-value indicates there is a poor fit, and we want a larger p-value, right? Again, but p-value is also sensitive to sample size, right? If you have a very large sample size, then it's very easy that you have a significant p-value. So this is why we need to combine chi-square test with other indices. For example, we also need to report Tucker-Lewis index and the comparative fit index, TLI and CFI. Both of the two indices are relative fit indices, which means that they compare the fit of your model to a null model or to a baseline model. So baseline model is a model with no relationship specified. And the threshold value should be equal to or greater than 0.95 for TLI and CFI. And we also need to report root mean square error of approximation, which is RMSEA. So this is absolute fit index. It measures how well your hypothetical model fits the data. It should be smaller than 0.06 to 0.08. So if your value of RMSEA falls within 0.05 to 0.08, it's also acceptable. Yeah, and this is a summary of different indices. So there are a lot more indices you can report. But basically, we categorize them into several categories. Like, for example, we have the absolute fit. We also have the comparative fit. We also, or relative fit. We also have parsimonious fit and other categories. So you need to report, the common practice is that you need to report indices from each of the category. At least you need to report indices from absolute fit and also comparative fit plus one RMSEA. But this indicator is also absolute fit, right? So this is how we report the indices. And here we also have parsimonious fit. So parsimonious fit is about the assessment of your model simplicity. So we always prefer a model that is both effective in explaining the relationships and simple, right? It needs to have a balance between effectiveness and simplicity. So if you want to say that your model can strike a balance between the two aspects, you can report some of the indices under parsimonious fit. Yeah, but most commonly we report indices from absolute fit and comparative fit and RMSEA. And how do we interpret? So here is an example, like imagine we have the results like this. We have the chi-square, we have the degrees of freedom, we have p-value, TLI, CFI, and RMSEA. So how do we interpret this? You can start from the chi-square test. So you can see that this chi-square test is very significant, right? So you can see it is a significant result, which means that there is a significant discrepancy between the observed data and your hypothetical model. But we also know that chi-square test is very sensitive to sample size. And we also consider additional indices. For example, TLI and CFI here, they both surpass the 0.95, right? Which means that it is a good fit by looking at TLI and CFI, and the RMSEA value 0.065 also falls within the acceptance range, right? So together, you use all the indices to say that these results suggest that even though there is a significant chi-square test, chi-square results, the SEM provides a reasonable and meaningful representation of the data. So because TLI, CFI, and RMSEA, they all support the adequacy of the model. This is how we interpret the model fits results by using different indices. And the goal of SEM is actually to assess the plausibility of your model as a whole, right? So sometimes if you find some of the indices do not fall within the acceptance range, it means that you might have a poor model fit. So you might need to revise some part of the model. You might to kind of drop some variables or revise some relationships in your model. But sometimes you also have the good model fit, right? So it means that your model is plausible, but we also need to be aware of equivalent model. So what is equivalent model? Equivalent model is that you have two different models, but you have the same model result. So for example, we have two models here. They're different. For example, on the left hand, we have the relationship from X to Y, but on the right hand, we have the relationship from Y to X. And if you run the two models in the software, it will give you the same results, right? Because the foundation of SEM is covariance, so they don't care about the directions. Like, is it from X to Y or is from Y to X? So back to the interpretation, sometimes even though you have very good fit results, you should be aware that SEM cannot validate the direction between variables. And it's totally possible that there is a reversed causality, right? So this is why we need to start from a very strong theory that can support the direction, or you complement it with the experimental design. And the key takeaways from this part, so you need to know that SEM is an umbrella term for different types of analysis. It can be single or multiple regression, it can be multivariate regression, or it can be path analysis, or it can be factor analysis, or it can be structural regression, right? And before you start doing SEM, you need to start with a theoretical model, and to start with the hypothesis. And most importantly, SEM is very useful to representing causal model, but you can't infer causality, or you can't demonstrate causality from using SEM alone. And this is the theoretical part about structural equation modeling. And next, I'm going to show you how to run SEM in R first, and then we can talk about how to run it in Amos. So you already have the R script, right? Like this.
Yes, they all have it, and the data as well.
Yeah. So you can open the R Studio first, and then you open the R script, CFA. So we start from the confirmatory factor analysis first. So the demo here is that we have three latent variables: visual, textual, and speed. And each of the latent variable has three observed variables, like x1, x2, and 3, and 2, x9. So we want to validate whether these items in the scale are reliable to measure each of the latent variable. So first, we need to know the syntax in Lavaan. So the main package we use in R to run SEM is Lavaan. And we use different syntax here, but most important are the first two lines. We use the tilde here as an operator to mean like predict. So we use it in regression analysis. For example, if you have y tilde x, the y is actually the dependent variable. You need to put on the left side of the symbol here, and then you need to put independent variable on the right side of the tilde. And we also have equal and tilde. So this is an operator for indicator. So it's used from latent variable to observe the variable in fact analysis. For example, we have this formula here. On the right, on the left side, f is actually a latent variable, and q, r, s here are observed variable. And these are the most important two syntax you need to remember. And we also explain like how do we which indices we need to report in CFA, how we interpret it. So we have two main dimensions in CF we need to look at. First is about convergent validity. It's about how closely these items are related to each other as one conceptual model. So like in this model, you want to see whether and to what extent these three observed variables are related to this latent variable. And we have three indices you can choose. Like we have Cronbach's alpha, it should be greater than 0.7. And we also have composite reliability. It also needs to be larger than 0.7. And we also have factor loadings, needs to be larger than 0.5. So these three indices are used to measure convergent validity. And we also have divergent validity. So it's on the is an opposite of convergent validity. Divergent validity is about how distinct one latent variable is from each other. So for example, here we have three latent variables, right? So the divergent validity is about how, to what extent can you differentiate visual from the other two latent variables? So then we use divergent validity to see it. And how do we check whether it has adequate divergent validity? We need to compare the square root of AVE. AVE is average variance extracted. We need to compare the square roots of this value to the correlations with other constructs, which means that in this case, we need to calculate the square roots of AVE value of visual here, and then we compare this value with visuals visuals correlation with textual and visuals correlation with speed. And this value, the square root of AVE value, needs to be larger than the correlation coefficients. And let's go back to RStudio. I hope you already opened the RStudio on your laptop. So we need to import the data first, right? And you run the first two lines here. Oh, first we need to set the working path, right? So you can do it by setting working directory to source file location, and then you run the first two lines. And then we have the data from here. You can see that it has 301 observations. It also includes 50 variables. And then we need to import Lavaan. If you haven't installed it, you can copy install.packages Lavaan to the console here, and then it can help you install the package. If you already have the package, then you just import the package here. And then the first step is that you need to specify the model, right? You need to describe the model. And our model is exactly like this: 3 latent variables plus 9 observed variables, right? So we need to put the latent variable on the left side of this symbol, plus equal and tilde. So on the left side is the latent variable, and on the right side is the observed variable that can measure this latent variable. So we have 3 latent variables: visual, textual, and speed. And then we put the corresponding observed variable on the right side. So you can import this data its model, and then we can use the CFA function directly from Lavaan. And then you need to put the model in. The model name is CFA model, and you need to put the data in. So we can run it here. And we already have it. And then you need to use summary function to check the result, right? And if you want standardized result, you just need to put a true value here, which means that you will have standardized result. And run it. And here it is. So the most important part is this part. Latent variables, we have 3, and then we have the standardized fact. This is actually the factor loading, the last column here, standardized all. So this is the factor loading from visual to X1. You can see it's 0.772, and this is for X2, this is for X3. So this is the factor loading. And if you still remember, the factor loading needs to be larger than 0.5, right? But we have a slightly lower number here, slightly lower than 0.5. But for the other observed variables, the factor loadings are all greater than 0.5. So in this case, you need to go back to, if you're using questionnaire, you need to go back to the questionnaire for visual, and you need to review this question. And you need to think about why it is not, why the factor loading is low. Like, is it because of the context? Is it because of the ambiguity in the language, in the wording, or is because other possibilities? And then you can decide whether you want to drop this item or you want to keep it. And this is how we calculate the factor loading. And then we still need to report some indices for convergent validity and divergent validity, right? And then we use another library here. It's called SEM tools. If you haven't installed this package, you can use the same syntax here. Install packages, and then you put SEM tools in the quotation mark. If you already have it, then you just import it. And then we just use the reliability function directly, and then you put the model in the CFA feed. And then we have the frame here, table frame here. So we have 3 latent variables: visual, textual, speed, and then the first line is alpha. So alpha means Chromebox alpha. So you can use it to check the convergent validity, right? So Chromebox alpha needs to be greater than 0.7. And for textual is good, but for visual and speed is slightly lower than 0.7. And we also have composite reliability here, right? So how to check composite reliability? We check the second line, omega here. Omega here is about composite reliability. So it also needs to be larger than 0.7, but again, visual and speed, their values are slightly lower than 0.7, right? And we also, and for divergent validity, we need to compare the square roots of AVE with the correlation coefficients, right? So AVE, we also have AVE, it's the last line. So we have the AVE value here, but you need to calculate the the square root value, and then you need to compare it with the correlation coefficients, right? So which means that we also need to have the correlation table here. And then how do you do this? First, you need to construct the new variables, because right now we only have the observed variable, and we need to add them up to construct the new variables like visual, textual, and speed. And then you use this block to construct 3 latent variables. And then you run it. And then we use this library to calculate the correlation. So you import this library, and then for this line, you can you need to put the variable names in. For example, I want to calculate the correlations among visual, textual, and speed. Then you just need to put their variable names in this parenthesis. And we run it. And this line is to specify the formats. So we want 2 digits. And you can specify, if you want 3, then you just put 3 here. So you want 2, then you just put 2 here. And this whole block here is actually to create a nice correlation matrix table and then export it to the Excel file. So it's easier to read, right? So you don't need to dive into the details here. You can, if you want to use this for your other projects, then you can copy the whole block and then you can replace the path here. Then we can have the correlation matrix table in Excel file here. So we already have it here, right? Correlation. So we can open this Excel file here. So you can see we have visual, textual, speed, and maybe you can add these variable names in the column A here. You can use transpose. And then you have the very nice correlation matrix table, right? And then we need to compare the square roots of AVE to the correlation coefficients, right? And then we can copy, we go back to this part, you copy the AVE value here. For example, for visual, this number, and copy this number to the Excel file. So we need to calculate the square root. Then we use the formula SQRT, and then you put the value here. And this is the square root of AVE value. And then we compare this value to the 2 coefficients, right? So you can see that this number is larger than these two values, which means that for visual, it has very good divergent validity, right? And then we do the same for textual and speed. So we just go back to R, and then we copy the AVE value here, and then we put it here. We then compare this value to the 2 coefficients. So it's also good for textual. And then we do the same for speed. And then compare this value to these 2. It's also good, right? So this is how we check the validity, divergent validity and convergent validity by looking at these different indices. And now I think you can experiment it in your own R Studio and see if you have any questions you want to ask or any error.
Did any of you try this, or are you trying the syntax, the R codes?
If you're on Zoom, you can give me a reaction, like, is it good? Then you give me a thumb up. And then if you have any question you want to ask, you can raise your hand. Then I can see if we have any questions on this part. So I will give you like 3 more minutes to try it on your own laptop, and then let me know if you have any questions. Just run this code and try to understand each step. The most important part is after import Lavaan, you need to specify a model and try to write this part on your own. You can delete this part and then you can try on your own and then see if you still have the result. Is everything good?
Does anyone have questions?
Is there
You can
any error popping up?
type in the chat line if you
Yeah.
prefer to type. I think I guess students can do the practice later, maybe.
Yeah.
I think surely you can just move on and show the rest of the things.
Yeah, sure. And then we go to the structural model. So like if you have a model like this, you want to run it, you want to use the structural regression in the SEM to test this model like this. And then how do you do this? Then for example, we have two latent variables here, right? So for example, we have R&D capability, and this latent variables have three observed variables, x1 to x3. And then we have another latent variable, which is collaborative innovation network. It also has three latent observed variable, M1 to M2 to M3. And we have another not latent, right? It's the observed variable. And we want to validate the measurement part for R&D capability and collaborative innovation network, as well as the structural part. It's more like a mediation model, right? From R&D to innovation network, and from innovation network to technology adoption rates. And we also have a path from R&D capability to technology adoption rates, right? So if you have such a model and you want to run it in SEM, how do you do this? We still use lavaan. We go back to another R script. It's called the structural model. So we still use lavaan. First, we need to clear this up, clear the old data file, and then we need to import the data, right? So you just need to run this line. Okay, so, oh, I need to check so this is actually an XLSX file. So I need to replace it, please. Run it, and then we have the data here. It has 500 observations and 7 variables, right? And then we need to import lavaan. And most important part is you need to specify the model, right? And remember, we have, go back to the model, we have the measurement part from R&D capability to X1 to X2 to X3. And then we also have the other latent variable. And then how do you write this? So we have 2 lines here. So these 2 lines are the measurement part. So it explains what are the observed variables for each of the 2 latent variables. We still use the same equal and tilde, right? And then this line is not mandatory for you to write. So this is just to fill in this space. So you can also delete it. And we also have the structural part. Structural part is about the relationship among these 3 main variables, right? R&D capability, collaborative innovation network, and technology adoption rates here. So how do you write the structural part? How many lines do you need to write? How many parts do you need to write? So one tip is to calculate how many dependent variables you have. For example, in this part, we have 2 dependent variables, right? One is collaborative innovation network. The other one is technology adoption rates. So if you have 2 dependent variables, then you need to write 2 paths, right? So the first path is from R&D to innovation network, right? The other parts, we need to focus on this dependent variable, right? We have two independent variables, collaborative innovation network and R&D capability. So in total, you need to write two lines. And here it is, but for the structural part, for the regression part, we only need to use one tilde, right? So these two lines are the regression part. And then you need to put the measurement model and regression model into one whole model. And then you use a quotation mark to capture this. And then we import this parts. And this is our model. And then we use the SEM function here, because this is not a CFA, right? This is not a confirmatory factor analysis. This is, we use another different function. And then we put the model in and put the data in, and then we run it. And then we use summary to check the results. We also use standardized results. Here it is. So this part, the very top part, is the, for example, we can see how many model parameters it estimated, right? Which means that it estimated 16 parameters, and we have 500 observations. And this part here, model test user model, this is the chi-square test. Test statistic, this line is the chi-square value. And then degrees of freedom and p-value is very significant. And then we also have CFI value here and TLI. And then if you go down, this is the RMSEA, this value, right? So these two numbers, CFI and TLI, they need to be larger than 0.95, which means that they're good. And for RMSEA is 0.063, so it falls within 0.06 to 0.08, so it means it's also good, right? And then we go to this part, latent variables. This is the measurement parts. We have two latent variables, R&D capabilities and innovation network, right? And then this column is their factor loadings. And for R&D, the three observed variables, they all have very good factor loadings, which are larger than 0.5, right? And then we have innovation network here, and it's three observed variables. The factor loadings here, they also greater than 0.5. It's good. And then this part is a structural part. So for example, these two lines means it's from R&D to innovation network, is from this variable to the other variable. So it's about this path. So the coefficient here is 0.474. And then when you draw the model here, you can actually put this number around this line to indicate the path coefficient. Yeah. And then we have the other path from R&D innovation network to this dependent variable to technology adoption rate. And the coefficient for R&D here is 0.261. And then you can copy this number to this one, to this path, right? From R&D to technology adoption rates. You put this number here to show the coefficient. And then we have innovation network to technology adoption rates, this number, and then you can put it here, right? So this is how we run the structural part and measurement part. And then if you want to see, for the measurement part, you want to see the Cronbach's alpha, composite reliability, and ABE value, right? Then you use the same tool, the SEM tools, and then you run reliability like this, and then you get the Cronbach's alpha omega value and ABE value, and you do the same like we did in CFA. You construct the new variables first, and then you run the regression, and then you calculate the mean square value of ABE, right? You calculate the square roots of ABE, and then you compared it with the correlation coefficients, right? So you can try to fill in this part by on your own, how to construct new variables for RMD and innovation network, and how to run correlations, and how to export it into an Excel file, and how you calculate the square roots of ABE, and how you compare it with the correlation coefficients. You can do it on your own here. Maybe give you another 3 minutes to do this.
Question from me, Shirley. Early on in the CFA analysis, maybe one or two of your standard all under the latent variables output was a bit low.
Yeah.
It was forgot, is it 0.4 something maybe? Would you prune the model by remove that? I think it was variable x2. Would you take it out? Would you remove it?
For example, we have one item that is lower, the factor loading is lower than 0.5, right?
Yes.
And this is 0.424. And then if you want to remove this, if you already check the question and you think it's not good to be included in the measurement, you want to exclude it. And then here, when you construct the new variable here, and then you just delete x2. So which means that in visual, you only have two questions, x1 and x3, and then you use this to construct new variables. For example, we can try it here. And then you do the same to run the correlations. And then you have new results. Or after you decide that you want to drop this x2, then maybe you want to run the CFA again, right? So here you can actually delete, in the CFA model, then you can delete x2, and then you run it again. You import a new model, and then you run this, and then, oh, sorry, here's an error. So visual textual suite, so I need to clear this. For example, now you only have x1 and x3 for visual, and this is your new model, right? And then you run it, and then you see the results again. Yeah, it's all good, which means that we'll only need to include x1 and x3 to construct visual, right? The factor loading is very good. And then you continue to do the same. You construct the visual without x2.
What does the literature say? What does the literature say when people are dropping certain items, despite that items has been previously validated by other researchers, and they found that x2 is a very integral part of a scale. Let's say x2 is an integral part of measuring visual. And then in our own study, we found that, hey, the x2 has a very low standard old figure. We need to remove it. And by removing the x2, it improves the outcome for this visual measurement. So what's the treatment in the literature with this?
I think there can be many possible reasons. For example, some people mention it's because of the contextual reasons. Like, for example, the questionnaire was developed initially in English, and then now you applied it in Chinese. So there might be difference in the process of translation, right? So it might be due to translation, then x2, the question on x2 loses some meaning. So it might be the contextual reason. And there are also other reasons, like I think the most commonly mentioned reason is the contextual reason. Like there's contextual differences between the questionnaire that was initially developed and in the context, and you apply the questionnaire in. So yeah. And then how do you decide whether you want to drop it? I think you need to provide very strong justification, like there are some evidence to show that people in your context might have some like disagreements in understanding this this question, and then you can decide, yeah, this can be a reason you can drop it, I think. Yeah. As long as you can find such justification from the past studies.
Excellent. Thanks.
Mm.
Other questions, anyone? If not, you can go ahead. Maybe we can finish earlier and let everyone
Yeah,
have a
sure.
chance to practice.
So this is R. How you write in R is very simple. You can just like this for structural model, you can just write simple lines, right? And then next, if you don't know how to do R coding, or if you struggle to write this R script, then you can always use Amos. So Amos, you don't need to code. So I need to switch to my another laptop, so I don't have the Amos in this laptop. But maybe for now, you can try to write the correlation part and construct new variable part on your own and see if you have any questions. And in the meanwhile, I will switch to the other laptop with Amos in.
One thing that I observe that people make mistakes, even including myself, when I just first learned how to use R, is that a lack of consistency in terms of what you write at the earlier part of the code with the later part of the code. For example, this called SEM model is a name that Shirley gave it. If you don't like this name, you can also give some other names. You could can give it, say, Taylor Swift 1 or whatever, right? If you like Taylor Swift. And then if you change it to Taylor Swift, which means that this Taylor Swift covers this latent, the construction and the regression. Here later, at the word SEM model, you need to also change it to Taylor Swift, the name of the person. If you still here, if over here you call it Taylor Swift, but in the later part you call it SM fit equals to SEM in bracket SEM model, it doesn't work. Your
exactly.
code cannot find what was it previously for this variable code. So
I think you need to, you need to understand these are different objects. Here in the environment, you can see this is the list for objects. For example, like I have, and I import, after I import this parts, right? And then you can see directly from the environment, this is an object. So this is the name of the object, and this is the content within. And then when you try to call different objects in the function, then you just go back to this environment and check the object name and which object you're going to put in the function. Yeah, this is how you can avoid the error because of the consistency. And I will stop sharing first. Yeah. So So can you see my screen right now?
Yes, you can start.
Yes, great. So we use the same data sets as we did in R, and we run this in Amos. So first, let's start with Amos.
So you all have access to Amos through the work desk. Yeah, you just click it.
Yeah, I have it. So this is the old file. We need to create a new file. And this is a new file, right? And then for confirmatory fact analysis, we need to specify the model. And in Amos, you need to draw the model. So how do you do this? So first we observed the model here. We have 3 data variables and 9 observed variables and 9 error items, right? And then we use this button here. And then we draw a round shape. This is latent variable. And if we continue to click on this round shape, it will pop up a observed variable and the error. And then we click 2 more times, it is the shape we want, right? And then if you want to rotate it, if you want to put the observed variable on the left, then you use this function here, this button. And then you click, and then this is the shape we want, right? And then we also have 2 other data variables with the same structure, right? And an easier way is to replicate this, duplicate this. And you can select all first, and then you use this button, duplicate objects, and then you drag to an empty space here, and then you drag again, and we have 3, right? And then you need to deselect. And next thing is you need to draw this double-headed arrows, right? So this is covariance. We need to use this button, draw covariances. We need to draw these 2, and then these 2, and this one. So here it is. And next step is you need to import the data, right? We need to use this button, select data file here. And then we go to file name, and it is CFA, right? CFA file. And we select sheet 1 and OK. And now you need to specify like which variable each of the shape represents, right? So we need to go to the list variables in data set. You click this button here, and we can see this is the variables in the data set. And then we want to specify like what variable this shape represents. And then this shape is actually x1, right? And then we drag x1 to this shape. And then you do the same for the remaining shapes, and x2, x3, x4. Five, 6, 7, 8, 9. And this is the observed variables, right? And then we need to name these latent variables here. You double click on the round shape, and then for example, this is textual. This is visual or textual. Visual, this should be visual. And this is textual. This is speed. And then we have this model, right? And next step, you need to specify the analysis properties. So we click this button here, and we use maximum likelihood. And if we go to output, then you can check the box here, standardized estimates. So we will have the standardized results in the outputs. And then we can try to click this button here, calculate estimates. Oh, we also need to name these error terms, items, right? Then we can use the plugin here. Go to plugins, and then it has a function name unobserved variables. So we click this, then it will name them automatically. And then we try to calculate this. We need to save this first. Save this file. So we use CFA1. So we have I think there are some error here. Here to analyze data with missing observations. We need to, when we specify the estimation here, analysis property, we need to check this box also, estimate means and intercepts. And then we run it again. And here it is. So this is the result, right? But it's unstandardized estimates. Then we can click standardized estimates. Then this is the standardized factor loading. It's actually the same result as we have seen in the R, right? So the only concern is here 0.42, and for the others they're all greater than 0.5. So this is factor loading, but we want to see, for example, like if you want to see the other details in the results, you can click view text. And in the view text, then we can see, for example, this is the degrees of freedom, this chi-square, and then estimates. Here we have different regression weights. And you want to, maybe right now you want to calculate the indices for convergent validity and divergent validity, right? We have different indices. And how do you do this? We can actually use another tool I already shared with you. It's an Excel file, the states tools package, this Excel template. So this template, if you go to the validity master, you can follow the instruction here. So for example, we need to paste the correlation tables into A1. So in the results, in the output window we have here, we need to find the correlation. We need to find the correlation table, right? So you need to go to estimates here, and then you expand it, and then scalars. And here we have correlations. And here's the correlation table. And we need to paste this table to the Excel file. First, we need to copy, and you can right click, and then you select copy, and then you go to this Excel template, and we need to paste it into A1, and then you paste it. And next, we need to paste standardized regression weights. Oh, we need to, sorry. I need to open this again. I need to copy this. And then we copy the standardized regression weights table. So we go back to the output window. We find the standardized regression weights here. And the same, we need to right click, copy, and we need to paste it into F1. So here is F1, and we paste it. and then we click this button. And here is the output table. CR is the composite reliability. So you can see the CR value for speed, for visual, for textual, and the AVE value here. And we have the correlation table, and on the diagonal is the square root of AVE. So you can compare the square root of AVE with the other correlation coefficients here. Yeah, so this is how we run the validity matrix, validity indices in using this template. And next is structural regression, right? Structural model. And if we want to run this model in AMOS, how do we do this? So first, let's close this. So first we need to create a new file. And we need to draw this model, right? So we do the same. We use this button to draw a latent variable, and we click on it. It has 3 observed variables here, and then we rotate it, and then we can select all, and then we duplicate. And for the endogenous variable, we have technology adoption rates. It is an observed variable, right? It is not like R&D capability or collaborative innovation network. They are latent variables. We have the observed variable here. So in this case, you need to draw this rectangle here. Rectangle means observed variable in AMOS. So we draw this, and then also needs an error items, right? So we use this button here, and here is an error here, and then we need to draw the arrows. So we need to draw an arrow like this, and so we have 2 dependent variables here in this model, this one and this one. But for example, like the latent variable here, but we also need an arrow term items here added to it, because it is a dependent variable, right? So we need to add another error here. So this is unobserved, right? So next thing is we need to import the data. So we select data, and we go to this one. Okay, and then we try to drag these variables into the shapes, right? This one, you need to deselect all, and then you can drag again. And here we have the another observed variable, right? We can also directly drag the tag here. So here it is, and then we need to name these latent variables. So we double click on the round shape, and then this is R&D, and then this is network, and we use plugin to name the unobserved variables. And here it is, and then we can specify the properties here. The output, we also want standardized estimates. If you want to estimate means or intercepts, you can check this box, but I think we're good for this case. And then we can click calculate. Yep, here it is. So this is the final results. We can see the factor loading, the past coefficients. So this is already standardized estimates. And then you want to check for example, the TLIs and the other indices, right, of the model fits. Then we go to view text here. This is the chi-square test. You can see the chi-square value, degrees of freedom, p-value. We can report this in the final result. And if we go to estimates, this is the standardized regression weights and their p-value. And we can go to model fit here. You can find, for example, TLI, CFI. We just look at the default model here. And then we can see RAM SEA value here. So this is this number, 0.03. And yeah, this is the results. And this is how we run AMIS, how we run structural regression AMIS. Yeah. Any questions? And if you want to calculate, for example, composite reliability or AVE, then you do the same as we did just now. You use the Excel template, and then you copy the correlation table, standardize the regression weights, and then you click this button. It will give you the results on CR value, on AVE, and the square root of AVE. Yes, and any questions you want to ask?
So for some of you who don't like coding,
Yeah.
if you don't like R coding using Amos, which is a more like graphical user interface, more like SPSS style of doing analysis, using this type of Amos is should be easier to do because you're just drawing and you don't need to go into specifying the syntax, the codes, because it runs it behind the algorithms. But what you need to make sure is just graphically it's correct according to the model that you are trying to test. That's excellent. Thank you so much,
Yep.
Shirley. Any questions?
Thank you. Any questions you want to ask?
Those online or those who are in the class, anything at all that you feel you're not very clear about? When you do model pruning, for example, the X2, in the previous one, the visual textual speed, if the result in the SEM was not very good, when you prune, would you follow the same? You just delete the arrows and then you rerun it again. Is that right?
Yeah. Yes. But you need to provide the justification, like why you want to delete it. Exactly. Instead of
that is something that the researcher need to explain in the methodology, that they deleted or removed something, and this is what is the reason. You need to justify. Yeah, that's very good.
I think there are
a lot more variation from this, right? Because some people are comparing data that are collected multiple times. There are more like there's a time effect and groups or subgroups analysis.
Subgroup analysis, you mean in this structural model?
Yeah, it depends on the complexity of the study. Some people are, for example, they collect data from 2 countries or 2 cities or 3 cities.
Yeah.
Yes. So there are more variation from all this.
Yeah, actually in Amos, they have the multi-group function that you can use. So if you have multi-groups, you want to compare, then you can explore a little bit on these buttons. So they have the multi-group analysis. You can try, but we only have 1 group for the demo data set, right? So if your data has multiple groups, then you can try different functions here. But the only thing for using Amos is that I think it's not as flexible as Lavaan. So in Lavaan, you can specify different paths. You can specify different variances among different variables. but for Amos, it has some rules. Like you need to draw like this. You need to have some, like they have the limits. For example, they have limited choice for example, like the discrepancy. They only have this 5 different types, but in Lavaan they have more choices. For example, you have categorical data for like one observed variable. Then you need to use different types of discrepancy, right? I think for Amos, the choice is very limited, but in Lavaan, you can explore more.
I really like Shirley's sharing today. I'll tell you what happened to us, me and my classmates in the PhD program when we learned SEM. Our professors were from America, and he's a mathematician. So when they teach this, the entire half day was mathematical equations. It's all the Greek letters. So after you sit there for 2 hours, your brain is full and you want to vomit. So it gives you a very strong distaste about this methodology. I like Shirley's approach, very practical and directly get you into the very hands-on, get you into directly how you can directly apply for the project. Remember, for your final project, your poster pitching, you have a data set and some code book. Actually, SEM is one of the possible tools that you could use to model whatever research model that you can draw from that data set. So it helps you directly learn how to use it and also how to interpret the results and which one is and even to create the tables. I think that is a very useful sharing today.
Yeah, so the students need to do a mini research project at the end of their study, right?
Yes,
okay,
they do. So we give them a data set and they need to come up with a poster. It's a poster pitching. So they need to find what is the research question based on those data set that we give them and specify a research model and specify the hypothesis and propose what kind of analytical tool that they will use, and then run the analysis and report the results and the conclusion and recommendation. So all in one poster.
Yeah. Well, it's very nice if you can use SEM, because I know that in psychology, like people use SEM a lot, right? So you can think about it. Yeah. But like
even in public policy, I know many scholars who are doing research using survey. If they want to test something beyond a very simple regression, they need to use SEM.
Yeah. But there are a lot of choices. Like we said, SEM is a family, right? It's a family of different statistical techniques. You can go for example, path analysis, and you can also go for like effect analysis, and you can combine the measurement model with the structural model and make it into one structural regression, right? So a lot of choices you can explore.
Yeah, and that's where I see using programming language like R or even Python, for those of you who will learn it, will be much more flexible, because actually if you run your analysis in R, you could move around using different packages to do a more sophisticated analysis. But if you have done your analysis in Amos like this, you cannot copy this to go to the next other software to run other analysis. But if you do it in R, you finish the correlation, you finish the regression, you can continue with doing SEM, CFA, and SEM. And then if you're not happy, you can continue to do other things, explore other things, or even do visualization. So that's the power. And we have a week on more on R next week. So hopefully this is not quite shocking for you in terms of R, because we're supposed to give you the R side first and then do the CFA, but Shirley have a gentle introduction to you about R from this analysis.
Yeah, I would recommend R for your own project.
Any questions, really? No questions? If no questions,
or if you have any ideas or any questions on your own like mini research project, you can also ask. Like if you want to use SEM, but you don't know how to, for example, structure the model, and you can also share your question.
But please don't ask questions about your final project poster pitching to Shirley, okay?
only on the SEM, related to SEM.
Questions? Any questions? Yeah. Johan. But I don't get the question. So in your survey, you use Q1, Q2, Q3, and then what happens next? Did you hear the question, Shirley?
No, it's silent.
Okay, maybe why don't you come and talk, and then let's hear.
Actually, I input my data in the R, and I found that there is a kind of syntax error. Like if I put the structure, like there is the observed variables, and they equal with my my original data, like econ, let me say equal with Q21, Q22, and it will be a syntax error because it could find the words like econ, like me say in my original data set.
Oh, I see. So you're using the CFA, right? And then when you write the path in the model specification, and then you need to give a different variable names, right? You can't use the same. For example, in your data set, you have x1, x2, x3 as the observable variables, and then you also have the latent variable that adds the three variables up, right? And then, for example, the latent variable is called x. And then when you run the CFA, when you write the model path, you can't use x directly because it will conflict with the variable in your original data set. You can use maybe another, like, for example, xx to differentiate with the variable, with the latent variable in your original data set. And this is the rule in Lavaan.
Okay. Should I?
Yeah, I don't know if I understand your question correctly, but I also had the same issue previously when I when I tried to run the confirmation effect analysis. Like, the rule is that you can't use the existing, for example, especially for the latent variable, you can't use the existing variable name in your original data set. You need to use a different, even though you are referring to the same variable, you can't use the variable, you can't use the variable name in your original data set.
So in conclusion, for the latent variable, you need to create a new name for that latent variable.
Yeah, especially when you run confirmatory effect analysis.
You can try again.
Yeah.
Good question. Good question. Yeah. Sometimes that is a very small issue and it doesn't want to recognize it. You just need to either you Google it or you ask somebody, and that solves the problem. That you remember, it's solved and you feel peaceful. You can sleep better.
Yes, exactly. Especially when you have like this tiny issue, it will cost you like hours to search for answers on Google. But if you have someone to ask directly, then it saves you a lot of time, right?
Yeah, but that is actually where the learning is. You learn.
Yeah, exactly.
If you ask Shirley, I'm sure she made a lot of mistakes. as much as I did, lots of mistakes. So why is this always fail? Why is this syntax not working? So you know something is wrong. And how you debug it is very important. How you debug it and find where the problem is with the code and how to fix it.
You can always use ChatGPT to help you decode, debug.
ChatGPT. If you
exactly.
have access to it, you could also try. And Shirley and I also have a little bit of fun of playing with that in ChatGPT and how
Yeah.
to run it in the codes.
Yeah, exactly. Especially when you code in R, it's very powerful for you to write the script. But I'm not sure about Amos. Maybe your ChatGPT is also good at Amos. But you can have a try. I remember they have for example, if you can still see my screen. They have the syntax here. Actually, you can use syntax to run Amos, right? So you can actually ask ChatGPT to write the syntax, and then you can copy it here, and then you can see if ChatGPT is good at this.
Nobody have tried it, but it's a good
Yeah. Yeah.
it's a good exploration. Thank you so much, Shirley. I think it's very late at your time there, and it's also 9 p.m. already here.
Yeah.
I think thank you so much. Let's give Shirley a very big applause for her time.
Thank you. Thank you,
Thank you,
Yanko,
Shirley.
for
Do you
inviting
have
me.
last words to say to them?
I hope by this lecture, you'll be able to know different types of SEM techniques and how to do it in R and Amos. Yeah, I hope you enjoyed the lecture.
Thank you. Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye. Bye. Bye.